thermal energy is very small, and there are many work. This is possibly one of the first papers which pointed it out very clearly, is that there is no vortex lattice melting, not even any disordering. You have vortex tau because of lattice which will remain up to the upper critical field. When you see this order-disorder transition, it's actually not driven by thermal energy. It's a competition between inter-vortex interaction and random pinning energy. And thermal energy plays a very small role. Why is that? Because when you take a crystal, you have a thickness of the crystal which is about, let's say, 0.1 to a few millimeters. And then if you calculate the condensation energy of the vortex for such a long vortex which is passing through the superconductor, you can calculate that, and this quantity will happen to be much larger than kT. So the vortex actually does not jump from side to side. On the other hand, this also tells you that if I reduce now the thickness of the superconductor to nanometers, I will reduce this condensation energy by 4 or 5 orders of magnitude, and now I have a hope that thermal fluctuation will start playing a significant role. So to verify that, some years back, we started investigating amorphous molybdenum germanium thin film, where we can make, of course, very thin films with moderate TC of 7 Kelvin or so. But in addition, here the pinning is very small. So we will have the energy scales in the problem will be intervortex interaction and thermal energy, with this random pinning energy being secondary. So it's not a major player here. This is a material that has been studied for many decades. However, no one did STM because the surface gets oxidized very fast. So we have this toy which is called an ultra-high vacuum suitcase. We grow the sample, directly take it in this suitcase, and then transfer to the STM without ever exposing it to air. Alright, this is the result. At 1 kilohertz state, you see a nice vortex lattice, and then as you increase field, you see more and more defects proliferating. This again does not tell you whether it's amorphous or liquid. So then we do this experiment. We take a small area, and then we keep on imaging this area continuously. So we keep on taking snapshots of this area, and I join the position of the vortices to find their trajectories. So when you have a solid here at 1 kilohertz state, you see that the vortex just moves a little bit about their mean position. At very high field, like 70 kilohertz state, now the vortex motion is completely random, and that is what we have studied as Brownian motion in school. However, in between, you have this state where the vortices have considerable motion, but if you see carefully over the long time scale, the motions are very directional. So they are moving, but not randomly as you can see here, but they are moving along the principal axis of the underlying hexagonal lattice. Now, when you have reduced the thickness of the superconductor, you have not just increased fluctuations, thermal fluctuations, but you have also done another thing. You have created a two-dimensional vortex lattice. So now the vortex lattice is considered of full point objects. And it was shown way back in the 70s, following the work of Berezinski, Costello, Fowles, but it was primarily shown by David Nelson, that you can have a two-step melting here, where you have a state which is called a hexatic fluid in between a solid and a liquid, which is a fluid state. It can flow, but it flows preferentially along certain direction because it maintains orientational order, though positional order is destroyed. And this was the first realization of hexatic fluid in any vortex system. Now, however, you can see that I can do this kind of imaging and track the motion of vortices only when the motion is very slow. And that means that if I now pass a current, the vortices will start moving and I will have dissipation, but the dissipation will be enormously small, and the estimated DC resistance will be of the order of 10 to the power minus 19 ohm meter. This would mean that there is not much implication for transport. And this was actually verified when we do resistance as a function of magnetic field at 300 milli we see nothing. But then when we do this measurement, we always avoid electromagnetic radiations from outside to get into my sample. So we put filters. If I start relaxing the corner frequency of this filter and start external stray electromagnetic radiation to leak in, we can see immediately there is a big difference between the solid and the liquid state. In the solid state, nothing much happens. Small amount of electromagnetic radiation which starts shaking the vortices doesn't do anything. But in the liquid state, the resistance increases rapidly, and now if from this difference you can find out the phase boundaries, the solid to hexatic, and here this increase corresponds to the hexatic to the isotropic liquid. So I can do this measurement and track as a function of temperature and magnetic field and construct a phase diagram. When you see this phase diagram, the striking thing is this. You have now a vortex solid which is only this tiny sliver here. Almost the entire phase diagram is vortex fluid state, either hexatic or isotropic liquid. Why are these kind of studies important? Very soon we found this in a vortex system, exactly the same sequence of transformation with essentially the same analysis was found from Lorentz microscopy in Skyrmion lattice. Then this was again refound by another group who studied it in more detail. It was also found in the vortex lattice in a rotating Bosch-Einstein condensate. So what I want to say is that the vortex system often provides you a platform to study phenomena that later can be investigated in more complex system. But now, and also the hexatic state is not the only state that has been seen. So some years back, these authors had reported a state which looked like a smectic vortex liquid. However, these images were at that time performed on small area, and therefore probably these results need to be further investigated in future. So this was on amorphous tungsten films. Okay. How am I doing with time? Okay, so now I have shown you earlier where we had the thermal energy and the intervortex interaction competing. Let me go to the other end of the spectrum where intervortex interaction is not very important, and I have thermal energy and random pinning energy competing. For that I need to increase the random pinning strength, and we use another amorphous superconductor called rhenium zirconium. And here in this amorphous superconductor, since spinning mainly comes from surface defects, if I reduce the thickness of the sample, then the surface to volume ratio increases and effectively my pinning increases. So I decrease the thickness from 20 nanometer to 5 nanometer. And here what I am showing you is the vortex state, the conductance maps in the vortex state for an ionium diselenide crystal and amorphous rhenium zirconium at the same temperature and magnetic field. The striking difference is this. Here you see the conductance minima corresponding to every vortex look almost identical. And that is what is expected. Every vortex is identical. However, here you see some of these minima are extremely deep and some of these minima are very shallow. Why does this happen? Let me explain this with this cartoon here. So if I have a conductance map like this and I bring my tip here where there is no vortex at all, I get a nice superconducting spectrum like this. If I now move my tip, if I move my tip here, where I have a vortex which is possibly jiggling around a little bit about its main position, you will find the core under the tip for most of the times, and since this core is a normal metal, your gap will be suppressed and your coherence peak will also be almost suppressed. If the vortex was completely static here, it will be completely flat, but since the vortex moves around a little bit, you might see a small feature. On the other hand, if I bring my tip here, where the vortex is jumping between these two sides, the vortex will see the tip will see the vortex core only 50% of the time, which means that you will have a spectrum which is in between these two. And this means that the intensity of the minima in the conductance map, it reflects the amount of time the vortex spends at a particular location. In other words, it's like the probability density. And these ideas came mainly from this paper, which is a density functional theory of flux line lattice melting. And this is the application of the famous density functional theory of melting by Yusuf and Ramakrishnan applied to vortices. All right. So now what we do, and I'll go a little fast here, you can calculate the motion path of the vortices. So you first find the minima, you find the nearest neighbor by Delaunay triangulation, you use some criteria and find the motion paths where these vortices are moving. However, we don't do this experiment once. We don't take one image, but we take a series of 10 or 20 images. And when we do this analysis for every frame, we see that this motion path changes with time. So over long scale, the motion path will be given by the sum of all these motion paths, which is shown here. But there is something else. When you look at these images, this is, for example, first, third, and seventh frame of a sequence of image, you see some of these vortices are static and they correspond to deep minima. But the shallow minima here, they not only change position, they also change intensity from frame to frame. This happens because of this. What I showed you earlier was what I call as complete hop. The vortex is jumping from one minima to the next minima, but every once in a while, it can also get trapped into an intermediate minima, which I call an incomplete hop. And then when it gets trapped here in the next image, this small minima will become the dominant minima, and this dominant minima will become the subdominant minima. Now these incomplete hops also results in motion, and to find that, you take all these images and you sum them. And then you can see now these motion paths from incomplete hops. You can again join them using some criteria, and this is your overall motion path, which consists of both complete and incomplete hops. Now when you do this as a function of temperature and magnetic field, the message is that we see even when we have increased the pinning energy, because your thermal fluctuation is large enough, we do not see a vortex solid anywhere, neither crystalline nor amorphous. We are always in this very inhomogeneous liquid state. Okay, so now we want to study a situation where I will have all these energies competing with each other. So I had earlier taken a limit where at least one of these was not important. So for that, what we do is that we go into something which is moderate pinning. Now this is the critical current density of the films that we have studied. You can see the very weakly pinned molybdenum germanium film is this one here, and the reasonably strongly pinned, this is the critical current density for the 5 nanometer rhenium zirconium. Now what I do is that I increase the thickness of this rhenium zirconium film to 20 nanometer. So effectively I reduce the pinning and I have a critical current density which is intermediate between the two. You have to look at low field. At high field there are additional effects that come in from interactions. Okay, what happens here? 460 millikelvin, I start at 3 kilohertz state, I have a inhomogeneous vortex liquid. I increase field. By the time I come to 20 kilohertz state, you see from something that was completely an inhomogeneous liquid and disordered, I have converted it into an ordered solid. Then if I increase field further, it disorders and I get eventually again an inhomogeneous vortex liquid. You can do various metrics. You can look at the number of vortices that are connected to motion path. Here it's almost, this fraction is 100%. It comes down to 0 at 20 kilohertz state, then again increases to 1. You can also look at the metric of orientational order, psi 6, and you can see this is completely disordered. It gets maximally ordered here at 20 kilohertz state and comes down. Alright, but this is as a function of magnetic field. So, what about as a function of temperature? I go to 3 kilohertz state, and at a low temperature, again, this is the same thing as we have seen before, but now I increase temperature. You can see as I increase temperature at 3 kilohertz state, I have almost a perfect vortex solid. So I have gone from an inhomogeneous liquid to a solid by increasing temperature, and from 3 to 4K, I suddenly have a melting. This is almost a first order abrupt melting, and here I cannot identify the minima, so I am just showing you the image. At 20 kilohertz state, of course, nothing much happens over this temperature range, it remains ordered, and 30 kilohertz state, you have just already the high field disordered state, the high field vortex liquid state, which becomes more mobile. But here what you have is completely counterintuitive, where increase of temperature has converted a liquid to a solid. Alright, now these, if you want a more pictorial visualization of this, then what you do is you don't do any such analysis, you just take the 20 frames that we have captured without filtering them, just the raw image, sum them. When the vortices are moving, your image will be blurred like this, and as when I increase magnetic field, let's say keeping the temperature 460 milliK, at 20 kilohertz state, the contrast has increased because the vortex is now ordered and vortices are not moving anymore. Same thing happens with temperature at 3 Kelvin, you can see you have an ordered vortex lattice. So this is a clinching proof of what I have shown you earlier with much more of analysis. So what is happening here? What is happening here is something which is called as inverse melting. This was predicted about 100 years back by Gustav Tammann. He searched for it, but he never found it in his lifetime. Later on, we have one example of inverse melting. That's the Pomeranchuk instability here in liquid helium-3. And here, for example, if you have liquid helium-3 at about 3.3 megapascal, and you increase temperature, you can see it goes fast from a liquid to a solid, and then back to a liquid. This has also been predicted for vortices. However, there was no real evidence of this before. There was some evidence in BISCO, but in BISCO you could never realize a true vortex liquid state. So continuously these experiments in BISCO, the only experiment that was done by applying what is called a dithering field and continuously shaking the vortices. That's, now if you shake, sand also flows, but sand is not a liquid. So I don't know whether I will call that inverse melting. Okay, we can now use the peak effect and construct the entire phase diagram. This is how the phase diagram looks. But what is more interesting is that there is a very fine interplay of these three energy scales here, because when I am at very strongly disordered, I have no inverse melting. When I am moderately clean for this 50 nanometer sample, where we have done all these experiments also, we have no inverse melting. It only happens at an intermediate level of pinning. Alright, here I will change gear now, and I'll ask the following question. That so far whatever I have shown you was essentially classical physics, classical statistical mechanical phenomena. However, are these vortices actually like classical objects, let's say like colloidal crystals, colloidal objects which are large and massive, or do they have a quantum nature? Now, if they have a quantum nature, then we know that in a solid where this vortex will be confined in the potential of the neighboring vortices, it should undergo zero-point fluctuation from the position on momentum uncertainty. Now, for this, we studied very carefully the vortex core spectroscopy. So, if I take the spectra along a line passing through a vortex in a very clean niobium diselenide crystal, you can see that at the core, I have earlier shown you that your vortex, your spectrum should be completely flat. It is flat, for example, here, when you take a slightly dirty sample. But if you have a very clean sample, you can also get this small peak, which is called the Karoli-Dogen Matricorn peak. And this is essentially because you are confining the normal electrons in 2 dimension within this vortex core, which is of the order of 10 nanometer or so. Now, you can get, for example, at the vortex core, this kind of small peak, or it can be flat. What we had observed some years back, when we took a molybdenum germanium film and did this measurement, we saw something that we could not explain in any simple way. What we see is that outside the vortex core, of course, you have this gap and coherence peak, but exactly at the center of the core, you also have this soft gap and in fact even this small coherence peak. Now this is not accounted for in any theory where the vortex is static. So therefore what we conjectured is probably the vortex are jiggling around, as I have already alluded once before, and in fact if I had a very fast measurement technique, I would see the spectra to be changing like this with time. But my measurement technique STM is slow, so it will average and I'll see something like this. The question is this motion caused by quantum uncertainty principle? Is it a zero-point motion or is it just a thermal motion? Now for that I need to extract the amplitude of this vibration. And this can be done, the way we did it was to first simulate the conductance map for a static vortex lattice. So these are all simulation of the conductance map at zero bias, at the coherence peak voltage, and you can see here that at zero bias, at the vortex core, the conductance goes to 1, the normalized conductance goes to 1, and similarly coherence peak also comes down to 1. Now, in order to simulate the shaking vortex, what we do is that we take this perfect vortex lattice and then we displace each of the vortex by a vector r, where this magnitude of r is a random number between 0 to a maximum value delta A, and then the angle is also a random number between 0 to 2 pi. So now we have, let's say, one such configuration, but with this protocol, we create 200 replica and we sum over it. So this is in effect ignoring retardation effect. So we have somewhat of a Born-Oppenheimer approximation. Now, when you do this, for example, A is my lattice constant and delta A is this maximum vibration amplitude. In my simulation, you see when delta A by A increases, you have gradually the zero bias conductance map, which again becomes, so it gets more diffuse, the conductance minima, and similarly the coherence peak map also gets more diffuse. Okay, so now what we can do, I can take a experimental data, this is at 450 millican 30 kilohertz step. I simulate this conductance map at zero bias and coherence peak with a given value of relative fluctuation delta A by A. And then I compare, let's say, this variation of zero bias conductance along this line, theory and experiment. You see that they match extremely well. The red line is what I have simulated, and the blue line is the data. At the coherence peak, there is a slight discrepancy. The amplitude of the variation matches very well. The absolute value has a difference, and this is primarily because we are ignoring circulating current effects. Nevertheless, I can use this zero bias conductance and do this fitting at various fields. And now what I see is at 450 millik, let's say delta A by A with magnetic field increases roughly like this. So this is the variation. So remember, this is the relative fluctuation amplitude with respect to the lattice constant. The question is, this variation, can it come from thermal or quantum fluctuation? For that, Surojit, the student who was involved in this, did a very interesting and very simple harmonic approximation calculation, from which you can show that if the amplitude of the thermal motion, means if you have thermal fluctuation, then delta A by A should depend on temperature but will be magnetic field independent. On the other hand, if you have 0-point fluctuation, then this delta A by A would be given by this quantity, which means it will go as h to the power 1/4. Now, after doing this calculation, we realized that this was calculated by Shubir Sachdev and his collaborators long back, and they had done a much better calculation than we had done, taken the full dispersion relation. But the final difference in this number was just, in this expression, was just a prefactor of 0.7. So there was no other difference with this simple calculation. This is the result. So now you can see this is h to the power 1/4. So you can see broadly there is noise. These extractions are not very accurate, but it follows h to the power 1/4 reasonably well. You can also take this prefactor here and then calculate what is the vortex mass. And we get a vortex mass of 36 electron mass. So this vortex mass is somewhat of a controversial quantity, but if you take the most popular theoretical estimate, which was by Schul in 65, we get 32 vortex electron mass, which is actually remarkably close. I don't know whether it's fortuitous. You can also find out the resonant frequency of this vibration, and that of course is magnetic field dependent. This omega naught is in terahertz. So therefore, it would be quite interesting to study this system with, let's say, microwave or terahertz spectroscopy, but microwave at, let's say, 100 or above, 100 gigahertz or above that. Okay, so I think this was one of the very strong proof that the vortex is actually a quantum entity. However, this year, about 2 months back in May, there was this paper, and this is a paper that I keep telling everyone about. I'm spectacularly impressed with it, where they actually did quantum coherent manipulation and readout of a superconducting vortex state. So what they did is, they had a strip, microstrip line resonator, and then you zero field cool, and you trap one or few vortices, very small number of vortices. Now these vortices, they will get trapped into pinning potentials, and since you have not one pinning potential but several pinning potential, let's say you have one pinning potential here and one potential here, it can be either in this state or this state. So you realize a two-level system. The question is, do these states hybridize quantum mechanically? Can there be tunneling between the two? Now, when they do the measurement with these trapped vortices, they see anti-level crossing and opening of a gap. This is not the most remarkable thing. The most remarkable thing is that Now they can do coherent manipulation. You can even see Rabi oscillation of the system between these two states. Now, the interpretation of where the two-level comes from is, you can possibly question it because you have many states inside. So why only two pinning potentials are participating? But the result is just spectacular. There is no question that there is a coherent phenomena going on here. And this would open the way to vortex-based qubit and vortex-based quantum information platforms. So with this, I am over my time, so I finish it. So we have shown that in nanometer thick superconducting field, you have vortex liquid that span a very large part of the parameter space. We see several new phenomena, formation of hexatics, mectic, vortex fluid, inverse melting, and so on. And we have also shown that vortices are quantum in nature. Now, if vortices are quantum in nature, you might immediately ask that is this liquid which passes down to very low temperature, is it really a thermal liquid or a quantum liquid? This is a question that has been asked to us many times. We don't know the answer, and this is what is left as an open question. Thank you.
Thank you, Pratap, for the excellent overview.
Thank you. Spectacular data. I wanted to ask you briefly about the vortex liquid that you claim at the and you asked the question already whether this can be a quantum vortex liquid. Do you have any data on the calorimetry that actually goes down in temperature and sees whether there is any residual entropy? Because there is the other possibility that this could be a novel vortex, quantum vortex glass that I want to understand whether it's excluded by any of your data.
Okay, now, so please let me first be honest. I'm an experimentalist, I look at my data. The intricate theoretical questions, I leave it for other people like you to answer it. However, we have so far not found, let's say, a very clinching evidence of the quantum, means the quantum vortex liquid. If it is just like a thermal vortex liquid, that's not very interesting. There has to be something special that happens there. But so far, we have not found anything of that kind yet. So I will just leave it at that. Now this other question of this glass that you are talking about, this is a matter that, this is also something that we have thought about. This inhomogeneous liquid, is it really a liquid or should we call it a glass? Now this I don't know, because this is a question of semantics. For me, a glass is a state where I have all these particles in a random configuration and they are all frozen in time. So since I don't have that, I call it an inhomogeneous liquid.
Do you have any measure of entropy?
The measure of entropy, unfortunately, I don't have at that moment. The main problem is that for thin film, doing real calorimetry is practically impossible because of the small mass. So we have to find some indirect way. If you have any idea, let me know.
So thanks for thought-provoking data, lots of things, and many questions about one remark. An old friend of mine, who is no more, Gradko Tesanovic, also my colleagues at Maxim, they predicted bosonic quantum Hall states at the very end.
I see.
Because bosons, these charged 2D bosons are effective in a magnetic field. So it's like the idea of the composite boson or composite linear. So they talked about, they predicted quantum Hall liquids at very high end.
Oh, I see. Yeah, we can chat about it. I have heard of this, but only briefly. I don't know any of the details.
Also, A.K. Rajagopal and Vasudevan, one of the they are all
okay. All right, we'll talk about that.
Yeah. So, my comment regarding the last conclusion, the vortices are quantum in nature. I think generalize, if you are making this conclusion generalized way, I think I have strong reservation because the vortices can have quantum properties if, as you rightly explained, that if there is 0 point fluctuation and h to the power 1/4 and so on. But in this is generic statement will be, I think,
Okay,
continuous.
so let me clarify this. When you have to ask the basic question, when does a particle display quantum nature? A particle, we don't display quantum nature. So to display quantum nature, you have to reduce the mass. And when the mass is very small, that is when the particle will start displaying quantum nature. So you will have much more hope of having a quantum nature displayed in thin film, because you see that mass of the vortex depends on the length of the vortex. And the length of the vortex is in a crystal is 10 to the power 5, 10 to the power maybe more, larger than in the films. So if you take very thin films, probably in all situations you will have a quantum vortex, because you have the mass which
Yeah,
is
I
small.
got a point. If this criteria matches, if your quantum fluctuation
Exactly.
is predominant, then
Last question.
Should-
So in this last experiment that you showed,
Yeah,
I think it is indeed the group from Karlsruhe.
I see.
Are their frequencies comparable and similar to your frequencies?
yes, this is very normal frequencies. Okay,
What is that frequency, terahertz or?
no, this is gigahertz frequency.
Okay.
Oh, no, frequency comparable to what the omega naught that I mentioned there?
Yes.
Probably yes, because this is terahertz, but you see there is h by hc2.
Also, they're looking at longer distance, so maybe.
Yeah, and they are doing the measurement at very low field, because microwave measurement, microwave strip-line resonator, the quality factor reduces very rapidly with field. So their fields are extremely low. I have not calculated, but probably it will be in the right order. Yes.
Maybe you have one more comment. Another criterion for quantum motion is that the dissipation should be small, dissipation from the normal core. And I guess you're looking at systems with small coherence lengths. That's also important to get to quantum.
I see. Yeah. So this is something. Okay, we can talk about it. I have a slight conceptual problem which I never understood. Is that in the ground state, even if I have dissipation, where will the energy go?
Well, okay. I mean, in energy go to the normal electrons, but you're right. Maybe they're trapped. You're probably right.
So
Let's take the last question.
So thanks,
Yeah.
Pratap, for this clear talk. So I think I have a query and the question regarding this, the robust phase what you have found through your STM measurements, right? But the question is that, do you really have any thermodynamic evidence there? Or any other microscopic evidence?
for which one are you talking
So
of?
this hexatic fluid state.
Hexatic fluid state, of course.
Because it's a very robust, it looks like
Yeah,
the field and...
as I have shown you, so this is not something I could show in very great detail, but you can already see here that we have this transport measurement. These are transport measurements, these are not STM measurements, where you can clearly see first you have the onset of resistance. When you have excitation on the system, you have the onset of resistance where you have a transition from solid to hexatic, and then the second transition, when the second transition happens, you suddenly have this fluid which was constrained to move in certain direction. Now it can move in all direction. So you have this rapid increase in the resistance again. So these kind of signatures, which are signatures from bulk transport, yes, we have that. And in fact, for every phenomena that we get through STM, this is something that we always look for. So this is one of the standard operating procedure in
I think
our
we can discuss
protocol.
later because we are running out of time.
Okay.
Thank you very much.
Okay.
Thank you. I'm sure there are a lot of questions, so we can interact with him during the coffee and later. And let's thank Pratap once again. Our next session.
Oh,
lovely.
thank you.